Watch the physical flight path of this drone. It climbs, dives, and loops, crossing over its own previous position in three-dimensional space. To engineer systems that navigate or track this kind of movement, we need precise mathematical models. But standard Cartesian mathematics attempts to map motion as a direct function, where a vertical position, y, depends exclusively on a horizontal position, x. This diagram shows an xy coordinate graph plotting a looping path that folds backward. As a vertical line sweeps across, it intersects two different y values. This violates the vertical line test, meaning the motion cannot be defined as y equals f of x. Pure Cartesian logic cannot describe systems that loop, orbit, or cycle. If we rely on it to predict physical reality, the model collapses the moment an object turns back on itself. The mathematical workaround requires us to decouple the x and y variables. We stop trying to define vertical position as a direct consequence of horizontal position. Instead, we introduce a third independent variable, a parameter. In engineering, this is usually time, t. This creates our parametric equations. The x-coordinate becomes its own independent function of time, x equals f of t, and the y-coordinate a separate function, y equals g of t. By structuring motion this way, we can calculate the exact rates of change, the complex mathematical derivatives of any looping physical trajectory. We will step through the derivation, identify a common calculation error, and observe the resulting formulas operating across three engineering domains. By subordinating physical space to time, engineers gain the mathematical leverage necessary to map any trajectory in the physical world. The first parametric derivative gives us the instantaneous rate of change of our trajectory, the slope of the curve at a specific millisecond in time. To find this, we apply the chain rule. We take the time derivative of y and divide it by the time derivative of x. This isolates dy over dx without needing to eliminate our time parameter. The process grows more complex when we calculate the second-order derivative, which defines the physical curvature and the acceleration along the path. It's tempting to assume the second derivative is simply the ratio of separate time derivatives. Since the first derivative remains a function of t, we differentiate with respect to time first. The chain rule then requires multiplying by the scaling factor dt over dx. Ignoring this nonlinear scaling factor mathematically erases the true physical curvature from the model, leading to inaccurate predictions of pathing and force. To test these equations, we must transition away from pure algebra and observe a physical object moving swiftly through three-dimensional space. This diagram plots a circular path with position vector r of t tracking a moving point. The first derivative gives the tangent velocity vector. The second derivative yields the inward spatial acceleration vector. Revealing it is the exact mathematical inverse of the initial position vector. This result provides the mathematical proof of centripetal acceleration, translating abstract geometry into measurable physical force. In aerospace engineering, standard Cartesian functions cannot describe the complex elliptical geometry required for orbital mechanics. Instead, satellites use time as their core tracking parameter. The first parametric derivative delivers the satellite's exact orbital velocity at any given millisecond. The second parametric derivative calculates the gravitational loads and g-forces pulling on the spacecraft. Structural engineers require this exact second-order derivative to determine the precise limits the spacecraft frame must endure to survive its own trajectory. We see the same logic in the invisible, cyclical phenomena of electrical power grids. Alternating current voltage and current are modeled parametrically as rotating vectors, known as phasors, governed by time. When current is plotted parametrically against voltage on an oscilloscope, it generates a complex looping Lissajous pattern. Calculating the second-order derivative reveals phase shifts and identifies the physical limits of capacitive and inductive grid elements. Without these calculations, undetected phase shifts can induce resonance, leading to localized power grid failures. These critical mathematical constraints are also central to automated control loops, where heavy physical robotic hardware navigates through exceptionally tight, complex manufacturing environments. Standard algebraic functions cannot model paths that turn back on themselves, forcing engineers to use parametric B-splines. The control loop uses the first derivative to determine the correct velocity vector, updating joint orientation in real time. The second derivative verifies C2 curvature continuity, ensuring the path geometry transitions perfectly smoothly. An error in this calculation produces jerk, an abrupt change in acceleration that can damage or shatter physical actuators. In robotics, calculating exact second-order curvature is the difference between fluid movement and mechanical failure. Manually calculating complex derivatives with the necessary scaling factors is too slow for modern engineering systems. Engineers deploy tools like the SymPy library in Python to solve these parametric equations symbolically, ensuring the chain rule logic is applied correctly. These formulas are then processed using NumPy, allowing the system to evaluate thousands of physical data points per second. This final computational step provides a geometric validation, ensuring the calculated vectors match the expected physical behavior. Bridging abstract calculus to automated code is what allows theoretical models to become functional engineering. We began by recognizing that Cartesian grids fail to describe movement that loops or cycles. Abandoning those coordinates allows us to map reality more accurately. Navigating these curves requires strict adherence to the chain rule, specifically accounting for the scaling factor required in second-order derivatives. Satellites in orbit, massive electrical grids, and automated robotic joints all rely on this same mathematical engine to function. This approach synchronizes the independent variable of time with the spatial and electrical behaviors of the system. Recognizing time as the primary driver allows engineers to accurately simulate and manage the complex motion within these high-precision domains.